Hello students, our next topic is Pushdown Automata. I have taken the slides from the internet, so the simplest way to explain, I found it very simple, so that is why I'm following these slides. So far we have seen deterministic finite automata, non-deterministic finite automata that is used for regular languages, and the languages that are not regular we need to see that might be a context-free languages. So, and for context-free languages we need to use context-free grammars, and that is so far we have seen, right? So what if we want that the finite automata that we have seen the DFAs and NFAs, so that should be enough capable to deal with non-regular languages as well. So this is one of the famous language that is used as a example for non-regular language, but it has so many other applications, or it can be interpreted in so many different problems. For example, you are writing a C language program, and there the number of brackets, like for example if you write a program, this bracket if starts, then it should be ended properly, right? So if it is used twice, then there should be it should be closed twice. So the curly bracket start two times, then the curly bracket ends two times. So it is something like this. Let's say A is equal to start curly bracket and B is equal to closed curly brackets or any types of brackets. So if these things we have to check the number of times A appears, the same number of times B should appear. So we cannot make any DFA or NFA to ensure that. We need a context-free grammar. But what if we could do some extension on finite automata, let's say DFA or NFAs, and it should be capable to do this. So this is like this is the example. We can see this is very similar to Pushdown, very similar to deterministic finite automata or NFA or DFA, where we have states and we have some graphs and we have a start state, we have a end state here, and we have a transitions, and we have some rules, transition function that lead us from one state to another state. So this looks very familiar with the DFA and NFAs. Besides, just the syntax is little different, right? Sorry, this is like something is very this is a little different. Before we have only strings. In pushdown automatas we have a syntax like this, where this is just a reading of one single alphabet. Let's say A, we are reading A, and in parallel to this we are maintaining one stack. In data structures and algorithms you might have studied the special data types, that is stack, that is used to solve so many problems, real-time problems or daily life problems using stacks. So in pushdown automata we maintain one thing extra, that is stack. What is stack? So let's start from the example. Pushdown automata is used to extract CFGs. So when we say that CFGs, context-free languages, so context-free languages is a superset of regular languages. It means it can accept regular and non-regular languages as well. So it has only one special data type used, that is stack. Stack is very easy and straightforward. This is like we can say that stack is a linear array, and let me denote array like this. So if you have a string, let's say A, B, C, and if you want to push this string into the stack, so you start from left to right, and first the alphabet is A. When you read A, you push. When you push, A is gone at the bottom of the stack. Then you read B, you push B, and then you read C. When you read the complete string, it goes into the stack ABC like this. And the second most famous function of the stack is pop. There are two possible operations we can do on the stack, is push and pop. When you push something, it goes at the top of the stack, and when you pop something, it removes whatever element is there at the top of the stack. For example, if you say pop, it will remove C. You cannot say that pop only A from the stack. Whenever the pop is called, it will remove the element at the top. So this is a very strict, let's say, guideline to handling the stack. So when you push, it is inserted at the top. When you set pop, the top element is removed. That is why it is also called first in and last out. First in, last out. So philo, first in, last out. Whatever is inserted at the first, like A was inserted first, but it will be the last element to be extracted. So where we can use stack is used so in so many applications and problems. Whoever students have used Windows 98 or XP, and in the DOS mode, though the recent DOS in Windows 10 is very smart, but in the DOS in back in Windows 98 or initial XP, we do not have arrow keys in DOS. So whatever you type, for example, I am typing cd some directory name, and if I mistake something, then I use backspace. So the backspace is basically implementation of stack. So whatever you have inserted, the last will be removed first. And there are so many other applications for problem solving. You can use stack. For example, if I want to invert the string, this like I want that whatever the string I have inserted should be inverted. What is the invert of this? CBA, right? So if I want this string to be inverted, then stack is used. First you push the whole string into the stack, and you start popping, and you print it. For example, if I just I just push this string into the stack, and I start popping, and when I start popping, the CBA will be printed, which is basically the inverse or the inversion of ABC. So anyway, you have already seen so many examples of stacks in your course at data structures and algorithms. So in the slides I have given some more examples, and this is the example. If I push A, B, C, so this is the example you can see. So how the stack is used with finite automata, and it makes a pushdown automata, and how it is useful we will see. So to define a pushdown automata, we need 7 things. First is like set of finite states, sigma, inputs, symbols, and we need we can use the same sigma for stack, but we can use a very entirely different set of symbols that should be inserted into the stack. So most of the time this is equal to sigma, but it doesn't have to. So you can use a very entirely different element that should be inserted into the stacks. So delta is the same, the transition function, like when you should switch from state 1 to, if you are in this state A, and if you go to state B, so when you can go to on state B. So this is a transition function we have seen already, but definitely how to write this function is little bit different than the DFA and NFA. We have a Q naught, we have a initial state, we have a F set of final state or accepting state, but we have one thing extra that is called initial stack symbol. So in computer programs, stack is like used in main memory, and you just put a bookmark, like this is the where my program starts. So this is just a very special symbol mostly used in stacks, that it just is an indicator that, oh, you started to use from this point. For example, stack is a very long array and you start from this, then this is just to keep a reference of where you started. You need a symbol. So the transition is defined like this: A, B, C. It means you read A and you pop B and you push C. It means whatever is before the comma is input string, input sigma, something the string is given. B is the pop element, whatever is here, it says pop B, right? And implies C means push C. So this is how the transition is read. The read A, pop B and push C. So let's take an example. For example, you are at the state Q node, and let's assume this is not an initial state, it is coming from some other state. So but you are currently at Q node, and whatever the string is a very long string, but you are reading the alphabet A. So this is the current state of the stack. So as we said that we will be maintaining a stack, so this is the current state of the stack, and this is the current state of a stack. And what is the transition? Transition says when you read A, you have to pop B and you have to push C. So you are reading A, this is the condition of the stack, and it says read A, you just read A, and it says pop B. Pop means remove B. So you remove B. So this is your current stack. After popping B, then you say push C. So this is the C is pushed into the stack. So after this transition, you are at Q1, and this is your current stack. I hope this example is clear. So it can be like we should do little more practice for this transition. This transition says read A, pop nothing. Epsilon means pop nothing, but push C, right? So you are reading A, this is your current stack status. It says read A, though we can pop something, but we are not popping anything. It says do nothing, don't pop anything, just push C. So this example is clear. You will be after reading A, you will move from Q0 to Q1, and this will be your stack after transition, and the stack is this is the stack before transition. And the third possibility is you read A, you pop B and you push nothing. So this is the possible transitions we can have. We read something, we pop something, but we don't push anything. Or in the previous example, we were reading something, we were not popping anything, but we were pushing something. And there could be a case we read nothing, but we pop something or we push something. So this is, in this example, we read A, we pop B and we push nothing. So this is our input symbol A, this is our current state B, but we pop B, the B is popped and nothing is pushed. So you move from Q0 to Q1, and this is your the state, the values in the stack after your transition. Alright, so there could be this case also. You read A, you pop nothing and you push nothing, you just exhaust your input symbol. So, and you move from Q0 to Q1. So the example is here. So if the previous all operations are clear, now we can easily start modeling a problem of this. And this is at the start of the lecture I have given A and B, and is a very famous problem, and it is used in parsing. If A is equal to this bracket and B is equal to this bracket, if it comes two times, then it should end. There should be two closing brackets as well. Okay, so this is how this is modeled. Like in DFAs, we did a lot of practice. If I give you a problem, you could make a DFA, but in this case the problem is this. This is the language we want to solve using PDA, and this is the solution. Of course, you need more practice to model solution for any language. For example, if I say make a push down automata for a language, this, it means anything can come at the start, but the string must end at 8 AB. This is a regular language, and you should be able to make a DFA or PDA solution to that. So this is just a bonus marks questions I will assign. Whoever practice to solve simple regular expression using PDAs will be given some extra marks, or maybe the one who want to score A grade should be focusing on that. So let's say you label this A. In the exam you have to use your name alphabets. You know that the trick I always use. And this is your input string. So you are always at the initial state, and this is the pointer is like you should be reading A. It says read nothing. You should, though if we conventionally we should be reading A. It says read nothing, pop nothing, and push the and sign. The and sign is basically the stack alphabet. That this is the bookmark. This is the indicate. This indicates that here this is the where our stack is starting. So we put $, and we come to the state B. Still we have not read anything. So because it says read nothing, pop nothing, but push $, and sign or $, or you can use whatever symbol you like. And when you are at B, there are two possibilities. Either, because your alphabets are A and B, so there are two possibilities. Either you will be encountered with A or B. So if A is there, what you have to do, you don't have to pop anything, but you have to push A into the stack. So when you read A, it says read A. It means I will whatever the string is read, I will just underline that. So when you read A, it says pop nothing but push A. It means whenever you encountered A in your string, push it into the stack. So there are 3 A's. 3 A's are pushed. So when your string comes, this is read, pushed, and this is read and pushed. As soon as you are encountered with B, so here the PDA start working. So B should be as many times as A has appeared, right? This is the basic thing we want to implement. So if it was 3 times, there should be 3 B's. If there are 4 A's, there should be a 4 B's. So whenever there is B, what you have to do, you have to start popping. Whenever you read B, you have to pop A and push nothing. So you are here, and it says whenever there is B, pop A. So this is popped. When, for example, now I'm saying this is popped. This is your top of the stack. Again, you read another B, you remove this, and this is the last B, and you read this, pop. So your pointer is at not $. Your string is empty. When your string is empty, let's assume you are now here, the string is empty. So there is no A, there is no B. If there is no A and there is no B, it means you are reading an empty string. If you read an empty string and there is a $, at to pop, for example, if I run a pop operation, what is there? A $, or and sign, or whatever my stack symbol is, then you push nothing. It means just remove this and you come to the final state. This is how it works. So in my next video, that will be a little short, I will give an example that is not actually accepted. I will maybe give this example, or I will give this example. These both strings should be rejected. It should never reach to the final state. So let's see in our next video.